Okay, so we're now on the final installment. This is the third time I've attempted to make this video, and it has failed as it's saved. So, yeah, uh, let's go for it. We had just used the raster calculator to come up with this nice little raster here, which is the distances within our lobe. Now what we're going to want to do is formulate an expression for the velocity at each of these pixels with which particles were ejected to get to that distance. And those particles were ejected at some angle. The distance, right, is what we've just struggled with calculating within this area, struggled or triumphed over. The angle is something that we can think about by looking at the topography of this lobe, and that might best be done by looking at Google Earth. So here we are in Google Earth. We're at Mono Lake. You can find us by searching Mono Lake. Here is the Mono Inyo volcanic chain. It ends at Panum Crater, which, as we discussed, has this very young lateral volcanic eruption that came out here. If you're curious as to why we're doing any of this, I encourage you to search YouTube to search YouTube for Mount St. Helens eruption and watch some of the footage of the lateral blast of Mount St. Helens. It's some exciting stuff, or scary when you think about it. So we want to know sort of how violent this eruption could have been, right? This is our favorite spot to send amateur photographers, right? Everybody likes to take pictures of the tufas. So we want to keep our amateur photographers safe, and to do that, as concerned scientists, we would like to estimate the velocity coming out of here. So you'll notice that Panum Crater is surrounded by this lobe, or this rim of what we will see to be volcanic material. Cool stuff, cool stuff. That lobe is much lower adjacent to, or the rim is much lower adjacent to the volcanic lobe than it is everywhere else, right? Here's the lobe here. Here it is on the backside. If we look at an orthogonal cross-section to that, oh, please don't crash. If we look at an orthogonal cross-section to that, we will see that on this side, right, the heights of the rim are pretty similar. And then it gets down to some pretty low elevation, and then we're in this little other blob of stuff that doesn't grow plants quite as well. And I'm going to say is maybe material that's been extruded after this stuff was deposited, right? To put something in a hole, we have to form the hole first, right? And our crater is a hole. So if this was originally some bowl, and we squirted this toothpaste up into it, right, then we can think about the initial bottom elevation of the bowl of doing something like what my mouse is doing here, where it gets down to something like 67-ish hundred feet. Now if we go back to our other topo profile, right, and our bowl is doing something like this, we'll see that here this is much lower than over here, right? I said that like 6 times already. If this used to be as high as that, but was knocked down by this lateral explosion that produced the lobe, right, then we can do a trig problem by going from the rim to here, right, about the middle point, which is a distance of about 1,000 feet, and realizing that the elevation gain from sort of the bottom of where the rim used to be, which I'll say is about 6,700 to about 6,800, right? We can think about that as sort of the trajectory of one of our ejected particles to knock this formerly high rim down. Then a trig problem can tell us something about the angle, and I'm going to guess that that's going to be something like 30 degrees. So now I want to use all that information, my formulated expression for velocity in terms of distance and the angle, and my ArcGIS raster of the distances to calculate velocity at every point. So to do that, I'll go back to raster calculator. I'm going to open it up, and I'm going to type in my expression, which might look something like, but I will tell you now, will not look exactly like square root. I'm going to add a parentheses, maybe gravity's in there, maybe gravity's going to be multiplied by the distance, right? And we want to make sure to do the distance of the lobe, right? Not the distance of distance, which will give us a huge raster, just a small raster. And then maybe that thing will be divided by the cosine of the angle. And I know from the internet that the cosine of the angle that I guessed, 30, is about 0.87. Cosine functions are in here, but I'm just going to type 0.87 in here. It's pissed at me. It's saying click error and warning icons for more information. Python syntax error, but that went away, so let's see if that's okay. As always, don't save this into the default folder. Choose your right folder. You can see that this is not the first time that I've done this, so let's try it one more time, shall we? PC vnot lobe 3. Let's hope this video actually works this time. And we'll see we now have some velocities from 50 to about 150. To display this, please create a contour map of these. You learned how to do that last week. Hopefully you remember how to do that. If not, search contour. I'd try a contour interval that gives you at least like 5 to 10 points in here. So for this one, right, 50 to 150, maybe I'd do a contour interval of 50. That would give me 10 different contours. After that, the thing that you want to do, I have already done this here, is you want to contour your velocities. You see I came up with something like 50 to 140 plus again. And then you're going to want to go in here and look at all these lineaments in here and map these and start thinking about what these are telling you, right? The direction of these with respect to the direction of the velocity contours, what that actually means. And it might be helpful to go back and think about this Euclidean distance, right? What is this doing? This is telling us the shortest distance to here, and our contours sort of parallel that. And then what's the relationship with these to that? And why might that be the case? And given that, what might these be? That's it, and goodbye.